Thanks a lot, and thank you for the invitation to AMLD Africa. It's a pleasure to be here. And yes, today we're going to be speaking about AI language models and their recent developments. So there is a lot indeed going on there. So as I was introduced, so I'm the co-founder and CEO of InstaDeep, an African AI startup. I'm also a Google machine learning developer expert. And today we're going to be discussing effectively interesting developments in language models. So we'll start by looking at basically AI language models and their impact as a whole. I will do a bit of a deep dive into the scaling aspect of language models, because this is quite important, and language models work well in particular because they scale, and there are recent developments there, and then provide a sort of concrete example through the notion of democratizing protein design in biology. So biotech is among the fields that is currently being disrupted by language models, and we'll give you some flavor what is happening there. So first, I mean, when we say language models, in many ways we're talking about transformers models, and transformers are a new model architecture that was invented and pioneered by Google back in 2017, but since then have become sort of like the key architecture on which is powering the recent progress in language models. Just to feed you sort of like the idea behind it, and this is something that's probably been discussed also by other speakers and will be further discussed today. The general idea is that in the past, when you were looking at, for example, at sequence modeling or the other, you would use models such as recurrent neural networks or LSTMs in particular, where effectively the dependency between two elements in a sentence, for example, would grow if they are very far apart from each other, which would make modeling hard, like long range dependencies, very complicated and sort of like unstable. With transformers and the notion of self-attention, you don't have this problem. The idea effectively is that every token or every element in the sentence is going to be directly connected to all the others. And this creates the notion of self-attention. And effectively, in a purely data-driven way, you can relate, particular element to others. So if we look at the sentence, the animal, the sentence you have here. If you look at, for example, it, you want to what is the relationship with it with other elements in the sentence. Well, it's the animal that you want to relate to, and this is exactly what you can learn in a purely data-driven way. So the notion is simple, but really like transformers have been sort of like progressing so quickly, and I want to sort of share with you my perspective on this, which is, I mean, we know that software is eating the world. These are famous words from Mark Andreessen, from like a famous venture VC investor in Silicon Valley. But when you think about it, deep learning is eating software. This is notion of software 2.0, or this notion of code written by data. And now you effectively have transformers and language models that are eating deep learning. So if you summarize that, it's like basically transformers are eating the world. And as a consequence, and this is why I wanted to talk about transformers and language models today, it's quite important to understand how they function, understand what's the impact today, but importantly for the future. And this is a bit the goal of what we're doing today. I have to say it is a remarkable thing that is happening, because typically when a field is successful, such as artificial intelligence and deep learning today, you tend to have specialization for different subtasks or problems or modalities. You would have different models. And this is indeed what we have seen for some time in deep learning, with convolutional neural networks specialized in vision, for example, recurrent neural networks and LSTM specialized for speech recognition or NLP. But what is amazing about what's been happening in recent years is the fact that transformers have effectively reunified the field. The notion of attention-based models has reunified the field. And this is quite rare and quite remarkable. The fact that these now cover many modalities is pretty remarkable. So if we look, for example, at vision, we used to use convolutional neural networks, and those are still very widely used. But the notion of self-attention is very powerful, and it can sometimes deliver better results, particularly when data scales, compared to CNNs. And this is despite the fact that CNNs have priors in their architecture, which are uniquely adapted to vision with different translation variances and the like. Well, the notion of attention is sufficiently powerful that you can really able to explicitly measure, for example, here, interactions between different elements in an image, or relate an image to text, for example, like in OpenAI's CLIP research paper, for example, and the like. So it's a very powerful principle, and indeed it is eating computer vision on top of NLP. But it's not just computer vision. In this recent example from OpenAI Codex, you basically see that OpenAI in this particular case took an evolution of GPT-3, but trained it on a public code available on GitHub. And what's amazing is that you get an ability to relate, say, NLP, or, for example, like tasks described in strings, and write directly like code which is going to be usable and actually giving good results. If you sample several times, you would get actually code that works. That is pretty amazing. And think about it. These are transformers eating programming. So my message here is that the technology behind language models is very powerful, and it is really tackling very different problems. This is also true in biology. If you look, for example, at proteins, which are essentially the engines of life, powering many major functions in your body, such as processing food, transporting, with enzymes, creating pathways for different functions, and so on and so forth. Also, like the immune system in your body. Well, there are actually sequences to start with. There are sequences of amino acids. So you could see that basically the engines of life are basically built on a language that has 20 different letters, and all the complexity come from there. Like the way you arrange those 20 different characters to build words or sentences creates incredible complexity through different 3D shapes and the like. And effectively, you can see it as I mentioned, as basically a language. 20 amino acids is a language. And so the same way, you have a sentence like the animal didn't cross the street because etc. You have the same with proteins, where you can relate a particular amino acid to another, and in particular, like how they create very complex 3D shapes. And so a remarkable breakthrough of that happened over the last few years is a breakthrough from Google DeepMind, where their AlphaFold 2 system, which uses attention in multiple ways and has been capable of effectively going from the sequence alone. So if I come back a few slides here, we on the left you have the sequence, basically like the different amino acids, and going from the sequence literally to the 3D structure, which is very complex. So here you see the experimental 3D structure versus the actually in silico computed or AI generated 3D structure, and you see they have a pretty good match up to atomic levels. This is a task, a problem, a scientific problem that was unsolved for 50 years. Yet, like language models, attention-based models have been able to solve it. So we live in truly extraordinary times where one model can effectively help write programs, can solve vision, solve NLP, and even solve complex structural biology. So I want to say a few words about what's been powering this revolution. Like, why is it the case? And the case is because those models scale very well. And actually, there's been recent work, or relatively recent work in particular, from OpenAI and Google, that shows that you can effectively model, for example, like test loss, validation test loss in machine learning explicitly. So you can see in when you're doing like a self-supervised task that involves transformer or attention-based models, you effectively can derive or empirically observe a power law relationship between the test loss and the amount of compute power you put on a given task, or the size of your data set, or the number of parameters. That is a pretty remarkable thing, because we tend to think of, test losses as, okay, it's just, a numerical value, whatever that is, and you just need to bring it down or prevent it from going up again in overfitting situations. But here you have an explicit formula, if you want, which is derived empirically, but is really solid between the different parameters, the number of parameters in the model, the number of tokens in the data set, and the explicit value of the loss. And this effectively is super powerful because it allows you to do several things when you look at it from a scaling perspective. It allows you, for example, to understand how much, for example, if you increase the parameter size of your model 8x, let's say, by how much should the data size increase to avoid overfitting? You would think that this is something like a trial and error thing, but effectively, researchers at OpenAI proved that this is fairly predictable, follows a power law, and effectively you can learn how to scale every parameter according to the others in a sort of like scientific way. And this is cool because you can avoid overfitting, and these are examples where you see here, if you increase too much the size parameter size of the model versus the size of the data, you get overfitting, but in a very predictable way, in a sense, which is very surprising. And this effectively gives you the first blueprints about how would I scale if I wanted to build really, really big models. But why build really big models? Not only because in general, like they're going to get you like a better test loss or better accuracy eventually, they turn out to be actually more sample efficient than small ones. So this is counterintuitive. You could imagine that a gigantic model, for example, would need a lot of data to start getting accurate results, but that's not the case. The bigger the model, actually, the more sample efficient, meaning that it will get to good results faster than a smaller model. And that is a first interesting thing. So generally, like when you see this, you would say, okay, this is true, you're more sample efficient, but actually you're using more compute. So somehow, it's very nice, but it's not very useful for me, given what I have and given the number, like the compute budget that I have. And this is where it gets very interesting too. It's actually that, if you have a given compute budget, the best way to use that compute budget is to build a large model. And again, in a sort of like predictable way, meaning that it's better to have a big model and not train to convergence, like sort of be, if you look at, the graph I'm showing here, be sort of like in the regime where the test loss is still sort of dropping almost vertically. This is where you're going to have the optimal sort of bang for your buck, or the optimal sort of like smallest possible test loss for the compute budget you have. Again, this is not a very intuitive thing, but but has been validated on these tasks. This is another reason why you need to scale models, because they are actually more effective for the same compute budget. And this is super interesting. And you can even derive relationships between how much you increase compute and versus data and the other. And effectively, like in a situation where you have, for example, a lot of data, you want to decide like how much you should increase the size of your models versus increasing the batch size versus increasing the number of time steps, like the numbers of gradient descents, for example. And you actually, have research that shows you that in general, it's better to make the model bigger, that this should be like where you're gonna increase in relative like sizes. This is where the model size would be the part which you would increase a lot. So why am I mentioning all these elements? Is for you to understand that there is a lot of science which is being developed, not just on the algorithms themselves, but on how they scale, why they deliver better results as they scale. And those results are very solid because we're now seeing the impact of the results on multiple areas. And what, a concrete example of this is that when, those researchers at OpenAI did the scaling study, this gave them the foundation to go and build super large models, such as OpenAI's GPT-3 that came in last year, which is a gigantic model with 175 billion parameters, trained over 400 billion word tokens taken from the internet and encyclopedia and other. But what I want to emphasize here is that the motivation for building such a large model, because this is really like at industrial scale, costs many millions of dollars to do. So why would you have done something like this? Is because you had strong sort of like scientific reasons to believe that this would give you a better result. And this is exactly what it did, because if you look, for example, at some of the examples, GPT-3 is a generative model and can get you, can literally build articles for you. Those articles are close to undistinguishable from real articles written by real journalists. And this is what you see on the graph here on the left. Your ability to discriminate between what is a real article written by a real journalist or a fake article or a generated article written by OpenAI's GPT-3 is getting close to 50%, which means it's not better than random. So this is to really show you the potential and power of those models. And last word maybe on GPT-3 is that, what I've shown you just before on OpenAI Codex is basically a direct evolution of GPT-3, just relating NLP on one side and code on the other. So research continues. And the theme of scaling transformers and language models is going to be a very big one. In research from this year, Google, through Switch Transformers, showed that you could actually get much larger models without investing more compute power. And the notion here is that you have gated systems where, if you look at like the attention layer in a transformer, you're keeping the attention layer the same, but if you look at the feed-forward layer that just comes on top of it, well, you have a choice between different feed-forward layers, and you have a gating system which is going to decide which one to take. So this means that when you're doing an inference, you're effectively using the same compute power, even though the model technically is much bigger. This is how we now have recent research that is coming in with trillion parameter scale models. So this, I hope, gives you a sense of like how incredible is the field at the moment. Recently, Stanford, for example, like the whole research department, AI research department of Stanford, decided to go all in on studying the property of those very large language models or transformer models, which they now call foundational models, understand where they are successful, where are the pitfalls, and how they can be improved. So this is really where the action is. And I wanted very briefly to give you a concrete example of what you can do and how you can innovate using the power of language models, which is coming directly from the work we do at InstaDeep. So we actually work in the field of biotech, among others, and we work directly with elite biotech companies such as BioNTech, the company behind the Pfizer-BioNTech vaccine. And through the work we did, we realized amazing opportunities and had great ideas about how we could democratize protein design. InstaDeep started literally with $2,000 and 2 laptops in North Africa. And there is always this notion with us about how are we going to make the work we do useful to many. And in this particular case, what could we do about protein design? So just to give you a sense, protein design is an incredibly complex problem with incredible combinatorial explosion. If you only align 4 amino acids, given that you have 20 choices for each one, you are already at 160,000 potential different proteins, which which is crazy. It is just 4 positions. In real life proteins, their length is typically more like 300 to 400 amino acids and can be more than 1,000 amino acids, for example, as is the case for the spike protein of SARS-CoV-2, for example. But let's say you take only 150 amino acids, which is a fairly small protein. And let's say you just say, okay, I can change only 10 positions to create a better protein. Well, this is still a solution space, which is bigger than the number of atoms in your body. This is just to give you a sense of how complicated the problem is. And this is how a protein looks like. Effectively, as I said, it's basically a sentence with words that are coming from a vocabulary that is only 20, like a vocabulary of 20 amino acids. So here you see actually a virus. And the idea in protein design is I'm looking for a specific property that I want to optimize. So I'm literally like navigating a very complex sort of solution space, and I'm looking for the right protein that's sequenced that's gonna fit my metric. And the reality is that it's not usually one metric. It's multiple metrics. You want a certain energy profile. You want this protein to be expressed or not attacked by the immune system. If you're looking at, for example, a therapeutic or a vaccine, so that's the notion of immunogenicity. You want it not to be toxic to humans, etc., etc. And you could potentially also have your own custom criteria. And this is this idea that led us to create DeepChain, which is world first in protein design created by InstaDeep. And DeepChain effectively sits at the intersection of AI innovation, biology expertise, and high performance computing. And importantly, is already delivering real results in the real world, which is super exciting. But the notion here is that we make it possible for anyone, including yourself, to actually build very powerful machine learning models to score proteins. And once you have multiple scores, you can optimize and find proteins that sort of like have a great performance on those different criteria. So how is this possible? Let's think about, typical what we call DeepChain app examples or scorer examples. Is you're either trying to classify a protein between different categories. It could be like human versus pathogen. So it's like safe protein versus something that is more harmful. But it could also be like a sort of like a predictor, as like a score on protein variability or its interaction with another protein or the like. So the interesting thing here is that language models have shown by training self-supervised on a very large amount of data, like think about all the proteins that are known to humanity, which is in the order of like 2 billion sequences, well, you can get good results. This is a research paper from Facebook AI from last year, where they trained self-supervised on 250 million proteins. And this is from sequence alone. And this is what's exciting. And they managed to get amazing results and sort of rediscover biological properties from sequence alone. So the idea that we're doing in DeepChain is very similar, but basically we use transfer learning. So imagine that you want to detect proteins from pathogens. You have those very large pre-trained models. What you're going to do is basically create a custom model on top, like a multi-layer perceptron, and use existing transformer model or the embeddings to build your prediction, and you get amazing results if you do this. So effectively, it's really the notion that you're going to only change, like in transformer learning for vision, you're only changing like the top layers to customize to your AI visual AI prediction task. That's the same notion. And in DeepChain, we can do this extremely quickly. You literally can build your app in a few minutes. And if you have embeddings, well, you actually don't need anything more than your laptop to create a very powerful model. So the notion here is that if I come back to 2 slides, you don't need to run this transformer model to train. If you have already embeddings on a significant protein dataset, you can directly take these embeddings and train your multi-layer perceptron. And this actually will be a very high quality model, because behind it, are these embeddings that have seen all of known biology, for example, which is super, super exciting. So I hope I give you a sense of how disruptive this is. Think about it. By using the tools, the free and open source tools we have at deepchain.bio, at app.deepchain.bio, you can literally, in a few minutes on your laptop, do work that usually would take a team of experts, GPU cluster, and potentially many months of work. So for us, this is the future. And this means that we can build lots of different criteria and then go and optimize and find specific proteins for the tasks we are looking at. And hopefully save lives in the process by building sort of like the personalized drugs or vaccines of the future, for example. So that's the perspective I wanted to share from InstaDeep. I wanted to mention that we are hiring. We've been nominated twice in the 100 most promising startups in the world. But importantly, what is important for us is this notion that, which is the last line here, that Africa can compete with the best and win. When I started the project in Africa, I never thought that this would be possible, yet here we are. We are building deep tech innovation, which is really important. And this is an example of how you can leverage language models to do really amazing things. So we live in an incredible time of disruption, and thank you for listening to me. I hope you found the presentation interesting, and in general, feel free to contact me either on my Twitter or shooting us an email. And if you're interested or excited by this type of problems, feel free to join us. We have many opportunities. So thanks a lot, everybody, and I'm very happy to take questions if you have any.
Thank you very much, Karim. It was really very inspiring, interesting, and also intriguing talk. You touched many points. Perhaps the first one that caught my eyes is the scalability of models, especially what you have said contradicts what I have learned in the first machine learning class, where I learned the Occam razor principle, the simpler the better for any application. But this is really intriguing, and it's also very interesting. I have a lot of interactions in the Q&A section. I will start with a first question from the audience, from Mohammed. So the results of GPT are truly impressive. However, the cost of training them is prohibitive. This will amplify just the inequality in accessing AI resources, and will hit Africa first. So the question is, what should we do to make these models accessible even when financial resources are limited? I think you also touched point with the last few slides with DeepChain and
yeah, this is a very, very good point, and this is really where the heart of our work is. With the DeepChain platform that we've built, for example, we're addressing directly this notion of elitist AI, or AI only for people who have a lot of compute, because effectively, large language models, you can see them as a strength if they are made available, and if it becomes super easy to add or to fine-tune those models to sort of customize them for your task. And this is exactly what we've done with DeepChain. But more generally, the idea is that no, you should not be afraid if you just have an internet connection and a laptop that you cannot be part of this, because the reality is many of those models are open source. And it's all about having the tools to build on top of them. So in a sense, you don't need to have the compute budget to do this, as long as you have the models and the few tools. And this is exactly something which is super important for us at InstaDeep, because we come from this world of limited resources, but there are ways to overcome this, and we're open sourcing these tools. So it's an exciting age, and yes, you can be part of innovation even without massive compute resources.
Great, thanks a lot. So perhaps a follow-up question. Does these large language model include a certain bias, and just adapting them to a certain context will inherently expose these biases, especially in Africa, for example, or in other low-resourced data sets, let's say?
No, absolutely. Definitely, there are biases, and this is a very important research topic at the moment. For example, like the reason why the AI research department of Stanford decided to go sort of all in on large models, or what they call foundational models, is because more research needs to be done to really understand the power of these models, but also the mistakes they make. This is particularly true when you take models like GPT-3 that are trained on the whole internet. Sort of like, despite all the best efforts of OpenAI, you're still going to find pitfalls. So how do you address this problem? To my sense, is with more research, but importantly, with more participation from different parties. So if we want to make sure that Africa is not going to be left behind, or sort of not going to be negatively biased against by those type of developments, we need to be part of the innovation. Because when you are part of the innovation, when you're working on your data sets for your specific problems, it's much more likely that the result is going to be balanced than, let's say, if all AI research happens in Silicon Valley, for example. So one of the solutions is more research, and this is happening. But to my sense, what is super important is the notion that as Africans, we should be active participants in this, so that we make sure that the product we develop, and in particular we develop for a part of the world, are relevant. If I take the example of biology, this is actually happening in the sense that now you have African bio companies such as 54Gene, for example, which was created in Lagos, Nigeria, which is making sure that sort of like data sets from Africa are included to design like the therapeutics of tomorrow, etc., so that there is no bias against it, in the sense that, okay, this is a drug that's been designed for particular populations elsewhere in the world. So this is very important, and the way to crack it is to increase our involvement in AI, not reduce it.